Welcome to the deep dive. I'm really glad you're joining us today because we are looking at something that is going to fundamentally change the way you look at a simple string of numbers.
Yeah, it really shifts your entire perspective.
It does. Today, we're exploring a single, remarkably dense source that you shared with us. It's a comprehensive overview of a concept called Polish notation.
Which is just a brilliant piece of history.
Right. And our mission for this deep dive is to explore how simply, rearranging the order of mathematical symbols completely eliminates the need for parentheses. We're going to look at how it revolutionized early formal logic and how it ultimately became the secret language of the computers we rely on every single day.
To really understand the origins of this, you have to imagine the intellectual atmosphere of a classic 1920s European library.
Oh, I love that visual.
Right. Picture towering oak bookshelves, academics debating in the halls, and tables covered in these beautifully complex, dusty logic manuscripts. That was the exact environment where this concept was born. Today, we are going to synthesize the history, the mechanics, and the modern applications of this notation, showing not just what it is, but why it actually matters to you.
I want to set the stage for you, the listener, for a second. Think about the last time you tried to write out a really complex math problem or a dense logic puzzle.
Or even just a long formula in Excel.
Yes, exactly.
Yeah.
Imagine you're typing a convoluted equation into a spreadsheet. You probably found yourself completely bogged down by brackets, parentheses, and the strict rules of the order of operations.
It gets messy fast.
It really does. You know the drill, making sure you have exactly 3 closed brackets at the end of your formula just to perfectly match the 3 open brackets at the beginning.
And if you miss one?
Right. A single typo breaks the entire formula. The software just yells at you. But what if there was a cleaner, completely linear way? What if you could just write the instructions straight across left to right and the math just worked?
That is the exact problem Polish notation solves. It strips away all of that visual clutter and relies purely on the sequence of the information.
Okay, let's unpack this. We all grew up on standard infix notation. That means the operator, the plus sign, the minus sign, the multiplication symbol, it's trapped right in the middle of the numbers it's operating on, like 1 plus 2.
Right. The operator is fixed in the center.
Exactly. But Polish notation, which is also called prefix notation, rips that operator out and puts it at the very front, so it becomes plus 1, 2.
And while putting the plus sign before the numbers might look a little strange for simple addition, its true power reveals itself when the equations become layered and highly complex.
Right. Let's look at a harder problem. Let's challenge you, the listener, to visualize this expression, open parenthesis, 5 minus 6, close parenthesis, multiplied by 7.
So standard infix notation.
Right. Because we use standard infix notation, we absolutely need those parentheses. If we drop them, the order of operations forces us to multiply the 6 and the 7 first, completely changing the math.
What's fascinating here is how Polish notation elegantly bypasses that entire problem. In this prefix system, the operator always precedes its operands.
So if I have that same equation, I'd start with the multiplication because that's the outermost operation. I write the multiplication sign first. But where does the subtraction go? If I just write multiply 5 minus 6, 7, that just looks like a jumbled mess of characters. How does the structure actually hold together without the brackets?
That's the trick. You work strictly by operations. You have your multiplication sign. It needs 2 operands. The first operand isn't a single number. It's the result of 5 minus 6.
Oh, I see.
So immediately after the multiplication sign, you write the subtraction sign followed by the 5 and the 6. Then finally, you put the 7 at the very end. The sequence becomes multiply minus 5, 6, 7.
And because every operator has a strict rule about how many numbers it needs, the brackets just vanish.
Precisely. That property is called its arity. A subtraction sign has an arity of 2. It always needs exactly 2 numbers following it. A multiplication sign also has an arity of 2. The structure regulates itself. No arbitrary order operations to memorize, and no hunting for missing parentheses.
But wait, what about order? If I'm multiplying, it doesn't really matter if I say 3 times 4 or 4 times 3, but division and subtraction are non-commutative. The order matters immensely. Does shifting everything to a linear line create confusion there?
Not at all. The source provides clear examples to ensure there is zero ambiguity. When dealing with non-commutative operations, the sequence of the operands directly follows how the operator takes its arguments, moving strictly left to right.
So the order is logged in.
Exactly. If you write the division symbol followed by 10 and then 5, it strictly means 10 divided by 5. If you write the minus sign followed by 7 and then 6, it strictly means you subtract 6 from 7. The action word dictates exactly what happens to the sequence that follows.
Imagine writing out instructions in your daily life
Yeah.
where the action always dictates exactly what follows, eliminating any ambiguity. You never have to backtrack or second guess which part of the instruction takes precedence. It's just a pure, linear flow of logic.
It is incredibly elegant. And to understand where this pursuit of pure logic came from, we have to travel back to the vibrant intellectual era of 1920s Poland.
The history here is fascinating. The Polish, in Polish notation, refers to the nationality of its inventor, a Ladyushin named Jan Łukasiewicz. He invented this parenthesis-free notation in 1924.
Right.
He actually mentioned it in a lithograph report in Polish in 1929 and then formally detailed it in a 1931 paper. It's gone by a few names over the years. You'll hear it called Normal Polish Notation, or NPN. Sometimes it's called Warsaw Notation or Eastern Notation.
We should provide a bit of historical context, too. While Łukasiewicz created the first linearly written parenthesis-free notation, he wasn't the only one chasing this kind of logical purity. Moses Schoenfinkel, whose work was edited by Heinrich Behmann in 1924, had the idea of eliminating parentheses in logic formulas.
Oh, interesting.
Yeah, and even further back, in 1879, Gottlob Frege proposed a visual parenthesis-free notation called Begriffsschrift.
But Frege's system was visual, right? It relied on two-dimensional lines and trees, which made it an absolute nightmare to actually typeset and print in a book.
Oh, completely impractical for mass printing.
Yeah. Łukasiewicz's version struck a chord because it was linear. It solved the typesetting problem for logic.
Exactly. It was so impactful that Alonzo Church, an absolute giant in mathematical logic, specifically praised Łukasiewicz's parenthesis-free notation in his classic 1944 book. Church called it worthy of remark, contrasting its elegance directly against the heavyweights of the time, Alfred North Whitehead and Bertrand Russell, and their notoriously dense masterwork, Principia Mathematica.
That is a huge endorsement. Principia Mathematica is famous for taking hundreds of pages of incredibly dense, bracket-heavy notation just to prove that 1 + 1 = 2.
It's infamous for it.
Yeah. To have Church point to Łukasiewicz's linear string and say, look at how much cleaner this is, speaks volumes.
It does. And we should note that Łukasiewicz didn't just use this notation for standard arithmetic. His primary focus was using it for complex formal logic. If you were to look at his original chalkboards, you wouldn't see math symbols. You'd see capital letters based on Polish words.
Let's break those down because the language connection is really interesting. For the concept of negation, like saying not true, he used the letter N, which stands for the Polish word negacja.
Makes perfect sense.
Right. For the material conditional, which is an if-then statement, he used C for implicacja. For disjunction, or, he used A for alternativa. And for conjunction, meaning and, he used K for koniemcia.
So you could write out massive, sprawling logical arguments just using strings of letters and variables with zero punctuation.
But that inevitably leads to some academic friction, doesn't it? When you start claiming letters for specific logical functions, what happens when someone else wants to expand the system?
This is where we run into a wonderfully quirky historical contradiction. Another logician by the name of Bocheski came along and expanded Łukasiewicz's system. He wanted to include all 16 binary connectives for classical propositional logic. But in doing so, his notation clashed horribly with Łukasiewicz's work in a different area called modal logic.
Because they were both trying to use the same letters for entirely different things. Łukasiewicz was using the letter M to mean possibility from the Polish word możliwość and the letter L to mean necessity from konieczność.
Precisely. But Bocheski, building his own massive extension of the very same parenthesis-free notation, decided to use M and L for completely different things, specifically non-implication and converse non-implication in classical logic. You had these two brilliant minds working in the exact same ecosystem, using the exact same letters to mean entirely different logical concepts. It highlights just how specialized and dense this field of study was becoming.
Here's where it gets really interesting, though. Because despite this being such a beautifully pure system, such an elegant way to write out logic without any brackets, human beings actually ended up hating Polish notation.
It is the ultimate irony. The system was designed by a human mind to make human logic more streamlined, but the human brain just doesn't process information that way very well.
It's fascinating because researchers later found that humans actually strongly prefer visual formatting. A 2011 paper by Martinez Nava, highlighted in the materials, points out that Polish notation fell into disuse, precisely because of how hostile it is for human reading. Our eyes naturally want to look at a spatial relationship.
We want that visual balance.
Yes, we want to see a number, an operator in the middle, and another number. That's how we balance concepts in our head.
Reading a string of prefix commands requires you to hold a tremendous amount of abstract information in your short-term memory. You have to stack all the operations in your mind before you ever get to the numbers they apply to. The research specifically highlights how incredibly difficult this makes reading for individuals with dyslexia.
Right. It removes all visual anchors. But you know what doesn't need visual anchors? A microchip.
If we connect this to the bigger picture, this failure in the realm of human cognition paved the way for its greatest triumph. While humans struggled immensely to read a sequential, parenthesis-free string of logic, computers absolutely loved it.
Humans need spatial cues, but a computer processor just wants a line of instructions it can chew through one by one. The material details what's called the evaluation algorithm, and this is where Polish notation becomes a superpower.
Let me explain how this algorithm works, as it is foundational to modern computing. Prefix expressions can be evaluated by a computer moving left to right or right to left, using something called a stack or a push-down store. Imagine a spring-loaded stack of cafeteria trays.
Okay, I like that.
You push a new tray down onto the top, and when you need one, you pop the top one off.
Okay, I can picture that, but how does the computer actually use that tray dispenser to do math?
The computer reads the input string token by token. A token being either an operator, like a plus sign, or an operand, like a number. Let's say it is evaluating from left to right. It pushes these tokens onto the stack one by one. It keeps pushing them down until it realizes that the top entries of the stack perfectly match the requirements, the arity of the operator sitting just below them.
So if the computer pushes down a multiplication sign, it knows it needs two numbers. It pushes down a 5, it pushes down a 6. Suddenly it says, wait, I have an operator and the exact number of operands it needs.
Exactly. Boom. It executes the multiplication right then and there, takes the 5, the 6, and the multiplication sign off the stack, and replaces them with the result 30. Then it just keeps reading the rest of the string.
But wait, that makes sense for simple math, but what happens when the computer hits a massive nested equation? Doesn't the stack get overloaded, holding all those operators waiting for numbers?
That's the brilliance of it. It doesn't overload because the moment any local condition is met, it collapses the data into a single result. The computer doesn't need to scan back and forth across a massive equation looking for brackets to figure out what to do first.
It just acts immediately.
Yes, it doesn't need the capability of arbitrary stack inspection. It just reads sequentially, pushes data onto the stack, and executes the moment the arity conditions are met.
It is incredibly efficient. This is why, for programming language interpreters, Polish notation is effortlessly parsed into abstract syntax trees.
Yes, an abstract syntax tree, or AST, is how a compiler understands code. It builds a tree where the operator is the root and the numbers are the branches. With normal human math, building that tree is computationally expensive. You have to program complex rules for precedence and parentheses.
Which takes time and memory.
Right. But Polish notation essentially is the tree, just written on a single line. It provides a perfect one-to-one mathematical representation of the code's structure.
Wow.
It strips away all the ambiguity of human language, leaving only the pure, executable logic.
Which brings us to where we are today. I want to ask you, the listener, have you ever tinkered with coding? Have you ever written a script to automate a task or used a highly advanced engineering calculator? Because if you have interacted with the ghost of Jan Łukasiewicz. Polish notation didn't die out. It just went behind the scenes.
The modern implementations are vast, and they show just how integral this logic remains.
Prefix notation is still heavily used in Lisp programming with its S-expressions. Now, it's worth noting that Lisp does use parentheses, which seems counterintuitive to what we've been discussing.
A bit of a paradox, yeah.
But that's a unique case because Lisp functions are treated as first-class data and are variadic, meaning they can take a variable number of arguments. The parentheses just help group them. But the core structural logic is still entirely prefix.
And we see it in data querying as well. If you work in IT, you are likely familiar with LDD filter syntax.
Yes. LDFP is a great example. If you need to search a massive company database for a specific user profile, you have to group complex logic together. Find someone in marketing, ND, who is either a manager or a director. LDAP uses prefix notation to cleanly encapsulate that logic without needing arbitrary precedence rules for AND versus OR.
It keeps it clean.
You also see it in the TCL programming language through its MathUp library, the AMBI programming language, and even CoffeeScript, which allows prefix notation for function calls.
But we also have to talk about its mirror image. While prefix notation puts the operator first, there is a variation called reverse Polish notation, or RPN. This is postfix notation. In RPN, the operators follow the operands. So instead of +1, 2, you write 1, 2, plus.
And RPN is everywhere in the hardware and stack-oriented software world.
It is heavily used in stack-oriented languages like PostScript, which is the foundational language that powers modern printing, and the Forth programming language. But its most famous application is arguably in Hewlett-Packard calculators.
If you have ever seen an engineer or a finance professional using a classic HP calculator, you were watching reverse Polish notation in action. They loved those machines because when you were calculating load-bearing stress or complex compound interest, you were dealing with massive formulas.
You'd get lost on a normal calculator.
Exactly. With a standard calculator, you need a notepad to write down intermediate results, or you need to perfectly track 8 levels of parentheses. With an RPN calculator, you just keep pushing numbers onto the stack and applying operations. It felt like you were manually driving the computer's processor.
It operates at a very low level. Postfix operators are even used by stack machines like the Burroughs large systems.
And right toward the end of our analysis, there is an incredibly dense mathematical rule that proves why all of this works so flawlessly. It's regarding the equation of returns.
Yes. It states that the number of return values of an expression equals the difference between the number of operands and the total arity of the operators minus the total number of return values of the operators.
So what does this all mean? That is a very dense sentence to process audibly. Let's actually test that to give you, the listener, a concrete idea of what's happening under the hood.
Let's track it in real time using our earlier example. Multiply minus 5, 6, 7. First, we count the operands, the numbers. We have 5, 6, and 7. That's 3 operands.
Okay, 3 operands. And then we look at the total arity of our operators. We have a multiplication sign and a subtraction sign. They each require 2 inputs, so the total arity is 4.
Exactly. And those 2 operators will eventually spit out 2 outputs, or 2 return values total. What that complex formula essentially proves is that when you map all those input requirements and output values together against the starting numbers, the entire sequence perfectly collapses to exactly one final answer.
It mathematically balances out. There are no dangling numbers left on the stack, and there are no missing variables causing a crash. It is a perfect, unbreakable mathematical loop. The structure inherently verifies itself without needing any outside punctuation to hold it together.
It is the ultimate expression of logical self-sufficiency.
And that brings us to the end of this journey. To summarize our deep dive today, we explored the brilliant, elegant concept of Polish notation. Born from the mind of Jan Łukasiewicz in 1920s Poland as a way to simplify and purify formal logic, it proved to be a bit too alien for the spatial processing brains of human beings.
It just didn't catch on for everyday writing.
Right. It was largely abandoned as a written language because it was just too hostile to human reading habits. But its pure, parenthesis-free, linear structure turned out to be the exact perfect match for the way computer processors operate, making it the foundational, highly efficient logic language that quietly powers modern computer parsing, algorithmic stacks, and engineering calculators to this day.
It is a remarkable testament to the idea that just because a system doesn't work well for human eyes doesn't mean it lacks intrinsic perfection.
I want to thank you, the listener, for coming along with us on this deep dive.
And as we conclude, I want to leave you with a final thought to mull over. This raises an important question. Today, we've seen how standard mathematical notation, with all its messy parentheses and precedence rules, is actually less efficient and less logical than a parenthesis-free linear string. We only use infix notation because it is what we are used to. It caters to our visual habits. So if we are still clinging to a less efficient math notation out of sheer habit, what other foundational systems in our daily lives, our workplaces, or our communication are we stubbornly holding on to out of comfort long after a vastly more logical alternative has been discovered?